and in this lecture we'll talk about once we have a joint distribution, what do we do with it? Then we'll introduce the concept of latent variables, and then eventually go to restricted Boltzmann machines and talk about learning in the case of restricted Boltzmann machines, which will eventually take us to sampling. Okay, so this is what is, I don't think this is all like a homogeneous lecture, but it's put into this lecture. We'll probably split it into 2 different lectures later on. But irrespective of that, I guess the overall story should be clear to all of you. So let's just again do a quick, not a recap, but a quick contextualization of what we have done so far. Right? So what we have done so far is we have focused on representations of joint distributions. Okay, and after representing, we have made a case that the number of parameters reduces, which should help learning. We have not actually done the learning part. Okay, we have always assumed that the learning is either done or someone has given it to us. Right? So representation is what we have spoken about in detail. Learning is something that we have ignored. And now the question which I'm asking you is, what do you do after learning? Is how do you use these joint distributions, right? So that's a question of inference. That once I have these parameters learned, once I have the factorization for the joint distribution, how do I make use of this joint distribution, right? So if you do a traditional course on graphical models, if you read the book or something, you will have 3 parts, which is representation, which is what we have largely focused on, then learning, which we'll eventually get to, and the third one is inference. Right? So far we have said that learning is essentially an oracle. All these factors and the click potentials were actually given to us by someone, and we were just using that as it is. But eventually we'll have to learn this. And this learning, we'll not do it in the context of general graphical models. We'll just do this in the context of RBMs. Right? So that's what we'll eventually get to. And inference is something which is general. So I'll just tell you, once you have a joint distribution, what are the different things that you could possibly do with a joint distribution. So let's focus on that in the first module of this lecture. Right? So using joint distributions for classification and sampling. So let us see what we mean by that. So consider a movie critic who writes reviews for movies. Okay? And we'll make a simplistic assumption that all the reviews that he or she writes are only these 5-word reviews. He or she just writes 5-word reviews, and here are some samples given to you. So this is your training data which is given to you. Okay? These are the reviews written by a particular reviewer. Now further, for the sake of simplicity, let us assume that this reviewer just has a vocabulary of 50 words. So whatever reviews he or she writes, he uses something from a set of 50 words that he knows and nothing beyond that. Right? So our vocabulary is restricted to size 50 words. Okay? So now, how do you treat this as, how do you define a joint distribution here? First of all, tell me what are your random variables. So this is where you need to put whatever you have learned to practice, right? So we have talked about X, Y, Z, all this in abstraction. Now I'm giving you a real world problem. Tell me, how are you going to use your knowledge? What's the graphical model is a secondary question. What are the random variables that you can consider here? Think about the process of generating a review, right? That the first word is a dash, the second word is a dash, the third word is a dash, where dash equal to random variable, right? So how many random variables do you have? 5. And what are you trying to learn? The joint distribution of P of x1, x2, up to x5. What does that actually mean? How many values can x1 take? 50. How many values can x2 take? And so on. So what's the size of this joint distribution? 50 raised to, or 5 raised to 50? 50 raised to 5. Just as 2 raised to 5, now this is 50 raised to 5, right? So the full distribution would have 50 raised to 5 values. Okay? Even for this toy example, you can see that's kind of intractable. Okay? So we know what are the random variables that we have, and we are interested in learning this joint distribution x1, x2, x3, x4, x5. Again, the secondary questions are now, or the second set of questions now are, what is the graphical model that you're going to use? How are you going to simplify this joint distribution into some factors, right? And once you have this, once you have the factors, once you have the joint distribution, what are you going to do with this joint distribution? Can you tell me what are you going to do with this joint distribution? Go back to the title of the module. I said classification and sampling, whatever that means. How many of you are able to think about this? See, eventually, of course, I'll tell you things, but that's not the point, right? I mean, you have to be able to think on your own. Others will just remain in abstractions, right? That we have n random variables, each of which can take 2 raised to n values and so on. Right? You have to apply these to real world problems, and this is as real as it gets, right? I mean, we all are interested in knowing what people post on Twitter, and this is exactly what people post on Twitter, right? And I want to learn that this next guy who is a political leader who will not be named, I want to automatically generate tweets from that political leader, right? How do I do that? We all know which political leader we are talking about. But we will not name him or her. Mostly him. Okay, so let's first talk about the graphical model, right? So we are going to talk about a very simplistic graphical model where we say that each word depends only on the previous 2 words. What is this problem that I am looking at here? Have you ever looked at this problem before? Have you ever looked at this problem before in lecture 10 or 11? Or lecture 10 was not RNNs. Oh, there are a lot of words here. What problem is this? Dash modeling. Language modeling, right? So given the previous k words, we want to predict the next word, right? You have to make these connections, otherwise what's the point? It's not that lecture 19 ho gaya, lecture 10 ho gaya. You have to keep making these connections, right? So, okay, so this is the problem of language modeling. And the moment I write the joint distribution as this factorization, what is the graphical model that I am considering? Can you draw the graphical model? How many nodes does the graphical model have? 5. How many edges does it have? I don't know actually, I'm trying to calculate, but yeah, you get the idea basically. Each node will have 2 parents, right? How many parents would each node have? 2 parents, except for the first 2 words, because you don't have x0 and x minus 1, right? So that's always the boundary case, is always the tricky one. So this is what it is, right? That this is the 0th word or the first word. Then the second word depends on the first word. The third word depends on both the first and second words. The fourth word again depends on the second and third word, and the fifth word depends on the third and fourth word. That's the graphical model which you have essentially captured, right? So even though we have formally introduced graphical models only now, we have been making this assumption and this factorization even when we were talking about language modeling, right? So this is the factorization, and this is a natural factorization, because even if you think about your own texting or typing, right? Once you know the last 2 words, you pretty much can predict what the next word is going to be. Or maybe if you know the last 3 words, you can largely predict what the next 2 words can be, or what the next word is going to be, right? So this is not a very unrealistic graphical model that you have chosen. So what are the factors of this graphical model? What are the factors of this joint distribution? How many factors does it have? 5, right? Okay. Now, how do you estimate these factors? So I said this learning part we'll do only in the context of RBMs, but let's just do it for this toy example because it's very simple to do it here. Let's consider one such factor, okay, and one assignment to that factor. So one of the factors here is that xi given xi minus 1 and xi minus 2, okay. Now consider one assignment to this factor, which is xi is equal to time, and the previous 2 words were waste of, which is not what this is, but how would you estimate this factor? I have given you the reviews from all the past reviews for this reviewer. How do you compute this problem? It is going to be a fraction of 2 counts. I mean, it's going to be a 1 count divided by another count. What are those 2 counts? The numerator is waste of money, okay, and denominator is waste of, okay, right? So this is how you'll estimate it. So now you know that you can estimate all the factors in this joint distribution given a corpus. I've given you one example, but you can do it for all of them. In particular, how would you estimate this? Your probability of x0 is equal to the, remember this is one of the factors in the joint distribution, right? So this is, this is not correct, right? We should write it as P of x0, P of x1 given x0, and then the product. Is it clear? I mean, because you always have this first root, then the next one, and then everything else has 2 parents, right? The first 0th word does not have a parent, the first word only has 1 parent, and after that everyone has 2 parents. Is that fine? Okay, fine. So how will you estimate P of x0 equal to the will count the number of times, the what? The appears as the first word in the review. Okay, is that fine? So you can compute all these factors. It's very easy to do in this simple case. Okay, okay, fine. So now we have a way of representing the distribution, and we also have a way of computing this table, which every column in this table is actually one of the factors that we are interested in. Is that fine? Now, given a review, classify if this review was written by this reviewer or not. How will you do that? And this is something that I'm interested in. Someone tells you that this is some statement which someone made, or this book is written by a particular author, and you want to know whether this is true, or this article was written by someone, and there could be various other applications of this, right? I mean, how would you decide, given this table and given a review, how will you decide whether this review was written by this author? And all the training data given to you was for one author. What will you compute? So what will you compute? Joint distribution of P of x1 equal to P of x2 equal to x3 equal to, please, I mean, have you had your breakfast? Okay. So this is exactly what you will compute, and you know that this joint distribution factorizes as these conditional distributions, and for each of these factors, you know how to compute this table. You have already computed this table. You just need to substitute the values from that table, and the answer which you get is 0.0005. Right? Of course, it requires some domain knowledge to know whether 0.005 is good enough or bad, right? Because it's a product of many factors, right? So even 0.005 is not bad actually. It's going to be a good value. How many of you get that? All these are decimals, right? 0 to 1. So you are multiplying 5 or 6 values, all of which are between 0 to 1. So 0.005 is actually not bad. So perhaps this is written by that. And that doesn't matter, because you'll have, what you could do is you could compute this probability for all the reviews that you have in your training data, and then based on that decide a threshold, right? So that's not the hard part. But the main thing is that given this joint distribution, you can compute this probability and then decide whether this was written by that or not. Is that fine? What's the other more interesting thing that you can do? Generate new reviews which look very similar to reviews written by this author. How would you do that? That's a good but incorrect answer, and very appropriate, because I'm also going to give the same answer and then correct it, of course. How are we going to generate new reviews? Someone said sampling from this distribution. Ignore the letter C part. How will you do it? How would you sample? What's the process that you'll use? Just imagine that you're writing down the reviews. You know that you have to write 5 words. How will you do it? What does sample that mean? How many of you understand how you'll do this? So now, how does the reviewer start his reviews? What is the first word that the reviewer chooses? How will you get the first word? For all the first words, you have this table P of x1 equal to W, right? So you know what's the probability of choosing for all the given 50 words in your vocabulary. You have assumed that your vocabulary is only 50 words. For each of these 50 words, you know what's the probability of x1 equal to the, what's the probability of x1 equal to movie, and so on. So just pick the one word which is the most likely word that the reviewer is going to use as the first word. So what's that word? Maybe the. Okay. So start writing the. Now how will you choose the second word? Given x1 is equal to the, find out x2 equal to W for all the 50 words and take the highest one. Right? This results in the movie. Okay. And then the third word, x3 equal to question mark, given x2 equal to movie and x1 equal to the. And again you get some maximum word and you do that. And that way you will continue. So I've done all this complex stuff and you have come up with one review for the reviewer. But your job, of course, is to keep posting more and more reviews from the same reviewer. Okay, so let's generate the next review. How will you do that? Let's start the process again. Select the max, the movie was really amazing. So you'll keep ending up with the same review again and again. No one is going to chat with your Twitter bot if you do this, right? So what will you do now? So what you did was not sampling. This was just picking up the most likely outcome. So what does sampling do actually? So the catch here is that, as I said, if you keep doing this, you'll generate the same review again and again. So instead of selecting the max, what we are going to do is we are going to sample from this distribution. What does sampling mean? Okay, so we'll see that. So suppose instead of 50, just for ease of illustration, there are 10 words in our vocabulary. We have computed the probability distribution for x1 equal to word, and x1 equal to the is the fraction of reviews having the as the first word, right? That's how we have computed this probability, right? Now similarly, we have computed all these other factors, right? So it's and so on, dot, dot, dot. We have computed all these other factors also. Now consider that we want to generate the third word in the review given the first two words of the review. What are the possibilities? How many possibilities are there? 10, right? We have come down from 50 to 10. So you could think of this as a 10-sided dice. And what you're going to do is you're going to roll this dice and just pick up the word which came at the top. However, unlike a fair dice where all the sides are equally likely, what kind of a dice do you have here? You have a biased or a loaded dice where the probability of a side showing up is proportional to the probability that you have computed in your table. Does that make sense? So you're not going to select the same face again and again, which is the maximum face. You're just going to roll it, but you know that when you roll it, the outcomes are going to show up with a certain probability, right? So it's possible that the max side shows up more often than the other sides, but the other sides also have a chance of showing up. And depending on whichever side shows up, you'll pick up that particular word. All this is fine. How do you do this? How do you write this as a program? How do you write this as a program? Assume you are given this table. How do you sample from a uniform distribution? What was I asking? How do you sample from a uniform distribution? So how do you implement a coin toss in Python? If you can implement a coin toss, rolling a dice is just one step ahead from there, right? How do you implement a coin toss? Suppose I tell you that the probability of heads is 0.4, right? And I ask you to generate a sequence of, keep tossing the coin so that I get the sequence heads, tails, and so on according to this probability. How will you do that? You guys have a sudden speech problem or something like that? You guys don't want to answer? How will you do that? Generate a random number between 0 to 1, so that's a uniform distribution. If the generated number is less than 0.4, say that less than equal to 0.4, say that the outcome was heads. It was greater than 0.4, say that the outcome was tails. Now instead of heads, tails, if you had a three-sided coin, whatever that means, how would you do it? I mean head, torso and tails probably, right? That's what it means. So how would you do it? Say the probability of heads is 0.4, the torso is 0.3 and 0.35 and 0.25. How would you do it? Again sample from this uniform distribution. If the number is less than 0.4, say heads. If it's between 0.4 to 0.75, say torso, and the other one is tails. You can extend it to 10 sides, right? So that's exactly what we are going to do here. I hope that's what is written here. You can go back and look at this code. So here we have a conditional probability distribution. Given the past two words were the movie, we have the probabilities assigned to all the 10 remaining. I don't know why I did this. Yeah, given the past two words, we have the probabilities that all the 10 words can take. So it's just like you had the probabilities for the 3 sides of the coin. You have the probabilities for the 10 sides of your dice. And now you just need to generate a random number and pick the value which falls in the right bucket. Does that make sense? Okay. So now if you run this code, at each time step we are not picking up the max value, but we are picking up a value depending on the probability of that particular value. So we are rolling the dice and maybe whichever side comes up, it's not going to be the max always, right? Okay. Now every run is now going to give us a new review. And of course some of them would not look very meaningful because you have sampled, right? Because it's possible that you picked up the least likely word at that point just out of luck, right? I mean, you roll the dice and that's the word which showed up. There is a probability of even the least likely word showing up. That's why some of these reviews wouldn't make sense. But using this, you can generate, useless reviews, right? So, okay, so that's what I meant by classification and sampling. So these are two things that you can do with a joint distribution. And so returning back to our story, what can we do with the joint distribution? The first thing is classification, the second thing is generation, and the third thing is actually a subset of generation, which is correct noisy reviews, right? So there is someone has, say, taken a pic from a paper of a review and sent it to you, and something in the pic is not visible, some words are not really clear. So you want to fill in the missing words given all the other words that you know, and that's exactly asking this question. Suppose the fifth word was blurred out, right? Then this is the question that you're asking about, that given the remaining four words, what's the most likely fifth word? Is that fine? Okay. So that was from the text domain. Now let's look at an example from the other domain, which is what many people are interested in doing today. Consider images which are in general m cross n pixels, but we'll consider they are square 32 cross 32 pixels, right? And we are looking at a lot of bedroom images because that's a data set called bedroom data sets and so on, right? So each pixel here is a random variable which can take values from 0 to 255, okay? Is that fine? So instead of that binary case, each pixel here is a random variable which takes on values from 0 to 255. And we have a total of 1024 random variables in this case, right? And the random variables are x1, x2 up to x1024. And what are we interested in? What are we interested in? The safest answer for this segment of the course is joint distribution, right? Why are we interested in the joint distribution? Just because we can. What will you do with the joint distribution? Classify whether this image is a bedroom image or some other image. In fact, these bedroom images could have been designed by a particular interior designer, and you can then classify whether this bedroom comes from the same interior designer, right? What else can you do? Become an interior designer. How? Oh, I thought by giving an entrance test and enrolling into a program or something. Okay, what will you do? Generate images from this distribution, right? And if someone has given you a design and someone dropped coffee on that, some portions are blurred, what can you do? Given all the other pixel values, you can decide what this is going to be, right? So the same set of things, if you're given a lot of bedroom images, just as you are given a lot of reviews by a particular author, you can learn this joint distribution. What is the factorization that you will choose for this joint distribution? In the text case, in the language modeling case, the natural choice was that each word depends on the previous two words or something like that. In this case, this is pixels. We have done convolutional neural networks already. That was a hint. So what's the neighborhood? What kind of a graphical model will you have? I already gave that answer. Directed, or we'll have a Markov network, okay? What are the factors? What are the dependencies? The dependencies give you the factors. Each pixel is a random variable. What is the assumption that you're going to make? It depends only on its neighbor. That's what makes sense in the case of images. That's what was the basis of using convolutional neural networks, right? Or the convolution operation, right? So we are going to use the Markov network that we'll consider is that each pixel depends on its neighborhood. The neighborhood is up to us to define whether we want to include the diagonal pixels or not. That's up to us to decide, right? And in fact, we could do it this way. So the joint distribution would factorize as these factors. Each factor here would correspond to this one maximal clique in the diagram that you have. And each clique corresponds to all the pixels. So I'm assuming that all these pixels are each other's neighbors, right? And that's completely up to me how to decide. I can do the worst case assumption that each pixel only depends on its immediate left neighbor or right neighbor, right? That's the same as what we decided in the case of words, that each word only depends on the previous words. I can do that kind of a assumption also. Whatever assumption I make, the distribution would factorize accordingly, okay? Now what is it that I need to learn here? These factors. These factors are very similar to conditional probability distributions, except that they are not conditional probability distributions. They give you the affinity between two pixels. What is the possibility that pixel 1 takes on the value 255 and pixel 2 also takes on the value 255? That's roughly what these factors tell you, assuming that the factors consider only 2 pixels, okay? Now what can you do with this joint distribution? Once you have this, you can take a new image, classify if it indeed is a bedroom image, right? And in this case, I meant to denote that 0.01 is actually a very low score, which I already contradicted before, but assume that this is a very low score and this is not a bedroom image. Generate new images, which would look like bedrooms, right? So now you have this. How will you generate this now? But unlike the word case, we do not have this very convenient thing, right? That you sample the first pixel, then you sample the second pixel based on the first pixel, third pixel based on the second and first. It's not like, because that's not how our factors are defined. So how are we going to sample from this distribution? So it's not very straightforward. That's the answer, right? For an undirected graphical model, it's not very straightforward to sample from this distribution. And that's what we're going to spend time on when we talk about restricted Boltzmann machines, which is an undirected graphical model, right? It's not very straightforward to do that, and we'll see we'll have to do something known as GIP sampling to do that, okay? And again, correct noisy images. And this, although I've written it as a separate bullet, this is essentially a subset of the generation of the image, right? You just need to generate one section of the image instead of generating all the pixels in the image, okay? So such models which try to learn this joint distribution P of X from the given data are known as generative models, right? And what we are interested in is deep generative models. So what would that mean? They're very profound generative models. So let's see, I'll try to see if you guys can answer this question, although this is going to come way later on, but at least it will give me some satisfaction that you've understood some stuff in this course. So what do joint distributions have? How are we representing them? As product of factors. Factors are the same as parameters. We need to learn these parameters. Whenever you want to learn something, okay, so sorry, we want to learn these factors. Whenever you want to learn something, what do we introduce? A parametric form of something, okay? Now can you tell me what deep generative models are going to be? Where this parametric form, so that means for every factor, you are going to define it as some function which has some parameters. Now can you tell me what a deep generative model would be, where this function would be a neural network, right? Does that make sense? Even if it doesn't, it will make sense after a week or so, right? So that's what we are interested in, deep generative models, hence this entire background on generative models.